Hello students, in this video I want to explain the preparation, properties and structure of the diborane. Diborane formula is B2H6. Now we discuss the preparation methods of the borane. Here, in order to prepare the borane or diborane, we have to add the hydrogen atoms to the boron. That means here we can take any compound of the boron, and by adding hydrogen atoms to that compound we can get the diborane. That means we have to reduce any compound of the boron in order to get the diborane. So now we go for the reduction of the boron trichloride with the lithium aluminum hydride. So first one is the reduction of the BCl3, that means boron trichloride with lithium aluminum hydride, LiAlH4. This is known as the lithium aluminum hydride. Here, so we will write BCl3 and LiAlH4, and we will write the compound required here. Here we want to prepare the diborane, so we will write here B2H6. And lithium reacts with chlorine and forms lithium chloride, and aluminium forms the aluminium chloride. So this reaction is very simple to balance. So here on the reactant side, hydrogen is present only in one reactant, and on the product side, hydrogen is present only in the diborane. So if you make the number of hydrogen atoms equal, then automatically the reaction becomes balanced. Here the number of hydrogen atoms is 4, and here the number of hydrogen atoms is 6. In order to make them equal, here we read the fourth table. 4 1s are 4, 4 2s are 8, and 4 3s are 12. And here we read the sixth table. 6 1s are 6, 6 2s are 12. So we have to multiply this with the 2, and we have to multiply this with 3. So 3 and 2. Now the number of hydrogen atom is 12, and here also 12. Now here in this case the number of boron atom is 4. So we here also we have to make the number of boron atoms 4. So we multiply it with the 4. Now here we have the 3 lithium atoms, and we have write here 3. Here we have the 3 aluminum atoms, so here also we write 3. Now we check the number of the chlorine atoms. Here 4 into 3, 12 chlorine atoms are there here. And here 3 and 3 into 3, 9. So 9, 3 plus 9, 12. So here this side also 12 chlorine atoms are there. So this equation is a balanced equation now. Now we go for the reduction of the boron trifluoride with sodium borohydride. Reduction of boron trifluoride with the sodium borohydride. This one is known as the sodium borohydride. So here we write the BF3 as well as the sodium borohydride. And here on this side we write the products. Products are B2H6, and the next product is the sodium fluoroborate, NaBF4. Okay, so this is also very simple to balance. Here hydrogen atoms number is 4, and here it is 6. So to balance this one, we have to multiply this with 3, and we have to multiply this with 2. Now 12 and 3 into 4, 12. And here the number of boron atom is 4 plus 2, 5. Now we have to balance the number of the fluorine atoms. Now the number of the fluorine atom is 4, and here it is 3. So we have to exchange these numbers. So we write here 4, and we write 3 here. Now we count the number of the boron atoms. Here 2 into 2, 4, and plus 3, 7 boron atoms are there. So here 4 plus 3, so 7 boron atoms are there here also. Now we count the number of the sodium atoms, 3 and 3. So this equation is also balanced equation. Now we go for the one more preparation method, that is the reduction of the boron trichloride with hydrogen gas in the presence of catalyst here. So reduction of the BCl3, boron trichloride, reduction of the BCl3 with hydrogen gas. So we write here BCl3, and we are directly reducing boron trichloride directly with the hydrogen gas in the presence of the copper aluminum alloy, which is maintained at the 450 degrees centigrade. Now the products are diborane B2H6 and hydrogen chloride B2H6 and HCl. So this is also very easy to balance this reaction. So here we have the two hydrogen boron atoms. So here we write 2 here, and we have the 6 chlorine atoms. So we write here 6Cl. 6 hydrogens plus 6 hydrogens. So we write the 2 hydrogen atoms on the reactant side. 12 hydrogen atoms means 6 hydrogen molecules. So like that, this is also very easy to balance the equation. Now we study the properties of the diborane. First of all, we go for the physical properties. Diborane is a gas. It is stable at low temperature, that too in the absence of the moisture and grease. Whenever it comes in contact with the moisture or grease, it explodes. And on heating, diborane is converted into other hydrides. For example, when diborane is heated to 180 degrees centigrade, it changes into the B10H14. B10H14 means decaborane. And when it is heated up to 100 degrees centigrade, it changes into B4H10. This is a tetraborane. And when tetraborane is heated up to 95 degrees centigrade, it changes into the again decaborane B10H14. Diborane on heating at 120 degrees centigrade, it changes into the B5H11. This is a pentaborane 11. And again pentaborane on heating at 60 degrees centigrade changes into the tetraborane. So these are the interconversions of the boron hydrides. Boron hydrides are collectively called as the boranes, and depending on the number of the boron atoms, we give the different names. So if the number of the boron atom is 5, we call it as the pentaborane. This is also pentaborane, this is also pentaborane. But here the number of hydrogen atom is 9 and the number of hydrogen atoms is 11. So we call it as the pentaborane 9 and we call it as the pentaborane 11. Now we go for the chemical properties of the diborane. First of all, we go for the reaction with the oxygen or air. Diborane, when comes in contact with the oxygen or air, it easily burns or explodes with the release of a lot of energy. And air itself changes into the boron trioxide and water. And we get lot of heat energy in this case. So it is also very easy to balance this reaction. Here we have 6 hydrogen atoms and here we have 2 only. So in order to balance, we will write here 3. Now the number of atoms, oxygen atoms is 6. 3 plus 3. So here we will write the 3. So like that, it is very easy. So as in this reaction we are getting a lot of energy, we use this diborane as a rocket fuel. Not only boranes, all anes. For example, binary compounds of hydrogen are known as the carbon are known as the alkanes, and we know very well that we use the alkanes as the fuels. For example, in the gas cylinders we have the pentane and butane as the fuels. So all anes, that means binary compounds of hydrogen, that means all hydrides are used as the fuels, because on burning these fuels we get lot of energy. Now we go for the reaction with water. So diborane explodes on reacting with the water. So we write that reaction B2H6 plus water. We get the boric acid H3BO3 plus hydrogen gas also releases here. So here we have the two hydrogen atoms, sorry, two boron atoms. So in order to balance this reaction, here we write 2 here. Now the number of oxygen atoms here, it is the 6. So to balance the reaction, we write the here 6H2. Now the number of hydrogen atoms here, 6 plus 12, 18. Here 6 are there. So still we will write the 12 hydrogen atoms. So here we write the 6. So like that, this is also very easy to balance. Now we go for the reaction with the base. Now diborane, when reacts with the bases like potassium hydroxide, forms a salt known as the metaborate. Here we get the potassium metaborate and water. Here we have the two boron atoms, sorry, hydrogen gas. Here we have the two boron atoms, so we write here 2BO2, 2KBO2. This is known as the potassium metaborate. Potassium metaborate. So here we have two, what is that, the potassium atoms. So we write 2KOH. And here 6 plus 2. Now we discuss about the reaction with acids. Diborane may react with acids like HCl, that means hydrochloric acid, and H2S4, sulfuric acid. When diborane reacts with hydrochloric acid, it forms monochlorodiborane, B2H5Cl, monochlorodiborane, and releases the hydrogen gas. In a similar way, diborane reacts with the sulfuric acid H2SO4 and forms diborane hydrogen sulfate, B2H5 HSO4 minus, and hydrogen gas. So like that, it forms the salts. Now we go for the reaction with the halogens. Halogens are fluorine, chlorine, bromine, and iodine. These elements are known as the halogens. Here we don't go for the reaction with fluorine and bromine because fluorine is highly reactive and iodine is very less reactive. So we go for the reaction with the chlorine. So when diborane reacts with the chlorine, one or all hydrogens may be replaced with the chlorine. So we get the different products here. This is very much similar to the reaction of chlorine with the ethane, B2H5Cl and HCl. Then this B2H5 monochlorodiborane may react with the another chlorine molecule and may form B2H4Cl2 and HCl. So like that, it may react until all the hydrogens are removed. So finally we can write the reaction like this also. B2H6 plus Cl2 gives rise the 2BCl3 plus 6HCl. So like that, we can write the reaction. Now we study the reaction of diborane with ammonia. Ammonia formula is NH3 and diborane formula is B2H6. B2H6 on reaction with ammonia forms different products depending on the conditions. So when diborane is reacted with ammonia at low temperatures, it forms a addition product which is known as the adduct. Addition product is called as the adduct. So the name of this adduct or addition product is diammoniate of diborane. Diammoniate of diborane. This is the first reaction in this one. And this diammoniate of diborane on heating gives another compound along with the release of the hydrogen gas. That another compound's formula is B3N3H6, and we get the hydrogen gas also. This compound is known as the inorganic compound or borazole or borazine. Borazole or borazine. Its structure is very much similar to the benzene, and here it has no carbon, so that's why this compound is known as the inorganic benzene. Inorganic benzene. Borazole or borazine is also called as inorganic benzene. Here, this is very simple to balance. Here we have the 3 boron atoms, and here we have the 2 boron atoms, and 2 nitrogen atoms. Here we have the 3 borons and 3 nitrogen atoms. So, in order to balance this equation, we have to simply exchange the numbers. So, we write here 3 and we write here 2. Now, the number of boron atoms is 6 and nitrogen atoms is also 6. 2 into 3, 6. 2 into 3, 6. Now we have to balance the hydrogen atoms. Here on this side we have the 12 hydrogen atoms, and here what is that, 6 plus 6, 12. 12 into 3, so 36 hydrogen atoms we have. So here already 12 are there. So when diborane reacts with the excess of ammonia, what happens? Let us see. So here we take the ammonia in excess amounts and we heat at a high temperature. So here we get a compound known as the boron nitride, along with the release of the hydrogen gas. Here, so we write here 2 and 6 plus 6, 12. So we write here 6 hydrogen atoms, and so here we may get n number of boron nitride. So it is a polymer, so we will write like this, polymer. So we write n here, and here also we, instead of writing 2, we write the 2n. So here 6n and 2 into 3, 6n. So we can write here 6n. Instead of simply writing 6, we write it 6n hydrogen molecules. Okay. And diborane on reaction with the limited supply of the ammonia at high temperature, again at high temperature. But here ammonia is in the limited supply. So here we directly get here borazole, B3N3H6, along with the release of the hydrogen gas. So here also very easy to balance this reaction. So here 3 and here number is 2, so we have to exchange the numbers like this. Now 6 nitrogen atoms are there, so we write here 6. Now 3 into 6, 18 plus 18, 36 hydrogen atoms are there on this side, and here 12 only are there, so we will write here 12H2. So 12 into 24 plus 12, 36 hydrogen atoms are present on the both the sides. So like that we can easily balance this equation. We have already learned that diborane is an electron deficient molecule. So we know very well that any electron deficient molecule accepts the electron pair from the other substances, and the substances which accept the electron pair from the other substances are called as the Lewis acid. So here diborane also acts as the Lewis acid due to its capacity to accept the electron pair from the other substances. Diborane accept the electron pairs from the other substance and form a coordinate covalent bond. The substances that are the products formed in the reaction are called as the adducts. Adduct means the addition products. For example, in this slide, diborane is reacting with the carbon monoxide at 100 degrees centigrade and 20 atmosphere pressure and is forming a addition product. Diborane reacts with the nitrogen compounds. We know very well that in nitrogen compounds, on the nitrogen atom lone electron pair is present. Due to this presence of this electron pair, nitrogenous compounds act as the Lewis bases and the diborane act as the Lewis acid. So, diborane reacts with these nitrogenous compounds and form the addition products. For example, in this slide, the reaction with tertiary amine and the reaction with pyridine is given. Ethers and thioethers also behave as the Lewis bases because on the oxygen atom as well as on the sulfur atoms, two lone electron pairs are present. As a result, they act as the Lewis bases. So, diborane reacts with these ethers and thioethers and form addition products. We discuss about the reaction of diborane with the olefins or alkenes. Olefins means nothing but alkenes. The simplest alkene is ethylene. Ethylene is the common name and ethene is the IUPAC name. Ethene is the IUPAC name. We can write diborane as the BH3 units. So we write here BH3 and the structure of the diborane is like that. Sorry, BH3 unit is like this, and here hydrogen is more electronegative than the boron. So we write partial negative charge on the hydrogen atoms like this, and boron is more electropositive than the hydrogen, so we write partial positive charge on it. So according to the as this is the simple symmetrical alkene, there here lies no problem in the addition of the BH3 units to the alkenes. But in case of the asymmetric alkenes, we have to follow the Markovnikov rule while adding the BH3 units to the alkenes, and there we have to remember this point. Now look here. Here what happens means, here one hydrogen comes here and one BH2 units attacks here. So we get CH3, CH2 and BH2 units. And here in this is alkyl diborane or alkyl borane. Here alkyl group is ethyl, so it is ethyl borane. Now it may add to the one more ethylene molecule like this. So now we get the CH3, CH2 taken to BH. Still it has one more hydrogen, so it reacts with the one more ethylene molecule like this. Now we have the trialkyl borane, CH3, and that means triethyl borane, CH3, CH taken 3 and B. So now it is known as the triethyl, that means trialkyl borane. Here alkyl boranes are less stable, and generally we carry out the reaction either in the aqueous medium or in the alcoholic medium. So immediately this trialkyl borane undergo reduction with the water and alcohol and other reducing agents like acids and give the alkanes. For example, look here, we can represent the trialkyl boranes as R3B or Br3. Now on reaction with water or on reaction with the acids like acetic acid, here they give the RH type alkanes and boric acid also. But this is a side product, we need not worry about this one. So we write 3H2 and here 2. So we write here 3 alkanes. And here boron triacetate. We need not worry about the side products. And this trialkyl boranes. For convenience, we take one example, that is ethyl borane, CH3 triethyl borane, taken 3 and B. When it is oxidized with the chromic acid, it undergoes oxidation and gives the acids. So this carbon undergoes oxidation and we get the acid. So here we get the acetic acid, CH3COOH. Then if this trialkyl borane or boranes are oxidized with the hydrogen peroxide in the presence of base, then we get the alcohols, CH3, CH2OH, ethyl alcohol. So here this bond breaks and OH groups attacks here, and we get the H3BO3 again. So By using the diborane, we can prepare alkanes. These are alkanes. We can prepare the carboxylic acids, and we can prepare the alcohol. So we can use this diborane as one of the most important compound to prepare the different organic compounds. While writing the reaction with the asymmetric alkenes propene or propylene, here it is propene. IUPAC name is propene, but whereas the common name is the propylene. So it is an unsymmetrical alkene because here this carbon is attached to the two hydrogen atoms, whereas this carbon is attached to the one hydrogen and one methyl group. So while writing the reaction with the unsymmetrical alkene, we have to follow the Markovnikov rule. Hydrogen is more electronegative than the hydrogen boron, so we will put partial negative charge, and on the boron we write partial positive charge. So according to Markovnikov rule, the nucleophile or anion of the addendum adds to the carbon which has the less number of the hydrogen atom. So this hydrogen comes to this carbon and BH2 units attached to this carbon. So now we get this product CH3, what is that, CH2 BH2. So here addition takes place according to the Markovnikov only, but we get the anti-Markovnikov product. This on further oxidation with hydrogen peroxide, we get the what is that 1-propanol. This is 1-propanol. But if the same propane or propylene is subjected to the hydrolysis in the presence of the acids like H2SO4, then we get the 2-propanol as the main product or major product. So here 2-propanol. So that is the difference here we have to remember. So similarly, we go for the one more reaction. Here, CH3 double bond CH2. This is 2-methyl propene. 2-methyl propene. So 2-methyl propene on reaction with diborane, and first one is reaction with diborane and then subject to hydrolysis with hydrogen peroxide in the presence of base, alkaline hydrolysis. Here in this case, what is that? We get the anti-Markovnikov product as the major product. So we get this one. 1, 2, 3. 2-methyl 1-propanol. 2-methyl propane 1-ol or 1-propanol as the major product. If this is subjected to the hydrolysis in the presence of acids like H2SO4, here we get this is anti-Markovnikov product. Anti-Markovnikov product. But whereas in this case we get the Markovnikov product as the major product. So here it is the 2-methyl 2-propanol. 2-propanol. So this is the Markovnikov product. So in order to prepare the anti-Markovnikov products in the organic synthesis, we can make use of the diborane. Now we discuss about the structure of diborane. Diborane formula is B2H6 and the central atom is boron or boron atoms. Atomic number of boron is 5, and the electronic configuration of the boron in the ground state is 1s2, 2s2, 2px1, 2py0, and 2pz0. Ground state means a state in which atoms have the lowest energy. Now, when energy supply goes into the excited state and we get a new electronic configuration, that is known as electronic configuration in the excited state, and that is 1s2, 2s1, 2px1, 2py0, and 2pz0. In the excited state, it undergoes sp3 hybridization. Here, one s orbital and three p orbitals combine and form four new orbitals, and those four new orbitals are called as sp3 hybrid orbitals. Here we have the four orbitals, but we have only three electrons. We have three electrons, but four orbitals. So here three sp3 orbitals have the three electrons, and we have one empty sp3 orbital at each boron atom. Now the s orbitals of the hydrogen atom combine with the sp3 orbitals of the boron atoms and form sigma bonds with the boron. So we have such four sigma bonds here, and these sigma bonds are called as the sigma sp3s bonds, because these bonds are formed between the sp3 orbital of the boron and s orbital of the hydrogen atom. So these bonds are known as sigma sp3s bonds. So we have the four sigma sp3s bonds, and here sp3 orbital containing one electron of one boron atom, hydrogen at s orbital of the hydrogen atom, and empty sp3 orbital of the another boron atom, and combine one more bond. This bonds is known as the now tau bond or banana bond. So we have two such banana bonds or tau bonds. Here these are normal covalent bonds. In normal covalent bonds, two electrons join or bind the two nuclei, one hydrogen and one boron and one hydrogen. Whereas in this case, two electrons bind the two boron atoms and the one hydrogen atom. So here two electrons join three nuclei. So this is a new type of bond, and we call it as the banana bond or tau bond. So in diborane, we have the four normal covalent bonds and two banana bonds. That means we have on the whole, six bonds. Normal covalent bonds means two centered two electron bonds, and banana bond or tau bond means three centered two electron bonds. Now this diborane is an electron deficient bond, because an electron deficient compound. Here, because diborane formula is very much similar to the ethane's formula C2H6. Diborane formula is the B2H6. Here we have these 7 bonds, and we require 14 electrons to form 7 bonds, and we are getting the 14 electrons from the 2 carbon atoms and 6 hydrogen atoms. Here carbon belongs to the fourth group, that means it provides the 4 electrons. That means 2 into 4 8, 2 into 4 8 plus 6 electrons from the hydrogen atom. So we get the 14 electrons, required number of the 14 electrons from the valence electrons of the atoms that are participating in the bond formation. Here but here we have the 12 electrons only. Here also the total number of atoms is 8, so we require the 7 bonds, but here we are having the only 2 electrons. So here 2 electrons are less than the required. So all such compounds which have less valence electrons than the required are known as the electron deficient compounds. So in order to explain the bond formation, here new concept of the banana or tau bond is introduced in the diborane. So diborane is an electron deficient compound. During the bond formation, sp3 will have one boron atom containing one electron, and empty sp3 will have another boron atom combine with the s orbital of the boron atom and form a banana shaped orbital. And this banana shaped orbital involves in the formation of the BHP bonds. So if you use the BHP bonds while writing or banana orbitals while writing the structure, we get this type of the structure. Now these hydrogens are known as the end hydrogens and are terminal hydrogens. Terminal hydrogens, and these are known as the bridge hydrogens. Bridge hydrogen atoms. This structure is supported by the NMR as well as the methylation. Here we have the evidences in support of the bridge structure. Here, now we go for the first evidence, that is the NMR evidence or Raman spectra evidence. In NMR, what is that? Ethane gives only one signal because here all hydrogens are same. Whereas in NMR and Raman spectra, diborane gives the two signals because we are having the two types of the bonds. Okay, na? So terminal BH bonds and bridge BHB bonds. So that's why we are getting two signals. And diborane on methylation with dimethyl sulfate substitutes only four hydrogen atoms, and it is not substituting the other two hydrogen atoms. That means these hydrogens must present between the two boron atoms. That means these two hydrogens must be bridge hydrogens. So these two evidences support the bridge structure of the diborane. Now we go for the dimensions of the diborane. The distance between the boron and hydrogen in the bridge bond is 1.33 angstroms or 133 picometers, and the BH bond distance in the terminal bonds is 119 picometers or 1.19 angstroms, and the distance between the two boron atoms is 1.77 angstroms or 177. Here these two BH2 groups lie in one plane, and these BHP bonds lie above and below the planes.